Okay, some announcement or reminders, quite a bit. Let's now go over them. You guys' written test from last Thursday is now being graded. I will keep you posted about the result. Okay, as soon as it's released, you can. I will bring the paper to the class, and then you can pick it up. And also, I will distribute the solution as well. You can take a look, and then you can feel free to speak to me about the test. If you got any concern, we can talk about it. But I'm hoping to get it done. Let's say within, let's say by the end of next week, the latest. Okay, so definitely before your exam, that's for sure. Right. Your project milestone number 2 has been released. The format is going to be very similar. So I'm going to send an e-class announcement tomorrow, 6 p.m. Wednesday, and then you will see a link to the Google Doc. You can actually sign up for the time. The time will just be the same, Friday and also Sunday. And then first come, first serve, right? Hopefully, if you want to stick to the time you actually got from last time, no problem, that's great. Shamru will be there. And also he's going to go over with you about what you did. Maybe since milestone number 1, it's been 2 weeks. So he also got your progress on his record. He also can check with you, and then he'll report to me if there's any concern. So take this more like an opportunity to really just make more progress and get some feedback from Shamru. If you want to speak to me, no problem. Just drop by office hour. We can definitely talk. And then basically milestone number 2, really the same thing. For milestone number 1, you actually got 3 example files to show. And for milestone number 2, you just got to show 5 additional files just to show different features about type checking, right? So you can show the different features you want to support, or different implementation, or different design, and Shamru can give you some feedback as well. Also prepare your questions to see how Shamru can help you. And then on your project instruction, I said I should really release by the end of today the project report template. I'm slightly delayed on that. I'll try to make this happen tomorrow, definitely before Thursday's class, because I also want to go over with you about the template. But you don't need to do anything now. So once I release the template, it's going to be a Word document, which you can feel free to modify the sections, but I'll give you more explicit rules. There might be certain sections you cannot really get rid of or rename. They got to be there. That's why it's a template. So I'll talk more about it definitely on Thursday. I can go over with you very quickly about the section organization for the report. Your assignment number 3, we are delayed. That's not your fault. It's my fault. So because I'm only going to start covering the top-down parsing today, but I would suggest we do 2 classes today and also Thursday, and then I'll release your assignment number 3. I'm going to push the deadline to as late as possible, so you guys definitely have enough time to do it. But the grading is going to be participation-based. You can definitely take some time to learn the material. I'll also give you a solution afterwards. Assignment number 3 is going to be actually quite an interesting programming challenge for you, because what we're going to start talking about today about top-down parsing, we're only going to talk about some pseudocode. It's not exactly like a programming language, but it's, I think it's formal enough for you to really see the idea about how to do top-down parsing. But the assignment itself is to really have you implement it precisely in Java. So that's going to be an interesting programming challenge for you. I think you'll be interested in doing that. But no pressure, because as long as you can submit your best attempt before the submission deadline, which I'll try to push as far as possible. Even the day before the exam, even that is okay. I can do that. So I just want you guys to maybe take enough time to do something about the assignment 3. I'll keep you posted, right? And then for our exam has been confirmed, I believe. I double check with the registrar office, so it's stable information. So it's going to be Wednesday, August 13th, and then it's going to be DB07. You guys know where DB is, right? Kind of far away from the campus, right? It's not winter time, so it should be a nice walk from York Lane. Anyway, so it's DB07. I believe it's basement, but you can double check. 9 a.m. Might be early for everybody, but just being fixed by the registrar office. It's going to be a 3-hour exam, and then it's going to be paper and pen, very similar to your written test. I may not have any example question for you. However, I promise I'll give you guys some tips about what you should really focus on more. Okay, on the last class, okay? Just give you some idea. All right, for the exam, but that's to come. For example, we didn't really actually cover the composite and visitor pattern in the written test. Very likely might be on the exam, right? For example, okay. So that's something I'll speak more about in the last class. Okay, and then we missed some classes because of the test and also other reason. So I'm going to somehow combine. There will be a topic which I want you to study also for the exam. I'm also going to put some questions on that. It's going to be more about bottom-up parsing. I do have some tutorial videos on that. I'll try to release it as soon as possible. So you do have another 3 weeks or so to really plan your time to gradually study that. You can study that in parallel to what we're doing now. It's kind of relevant to what we're doing in top-down parsing, but it's just something additional. Okay, so that one is going to make up the time and also study some topics for the exam. Okay, so definitely it's going to be worth your time doing it. I'll try to release this lecture as soon as I can, so you definitely got at least 3 weeks to do it. Okay, all right, guys, any questions about the course? Yes. Yes, that's correct. Pen and paper, no data sheets. In some way, no data sheets, because I think for the nature of this course, it's better not to have data sheets. Because if you do have data sheets, I cannot really put in any definition question or things like that, right? So you'd be much more open-ended, which might be a little more challenging for you guys. So I think without data sheet might be better. That's a decision I make anyway. So no data sheets, paper and pen. I will provide you guys with sketch paper, so you don't need to bring your own. You can write in pen or pencil. Yeah, things like that.
And a second one. I'm wondering, there were some questions where you had a cap of 50% if you argued the wrong way for a given question.
The cap? Sorry, what do you mean?
There were some questions on the written where you had to argue if a given case was correct or not. Right?
Yeah.
And if you argued incorrectly, you would be capped at 50% of the question. Would there be some similar questions?
Oh, I see what you mean. It could be similar, but I think you can expect the exam itself might be a little bit more longer answer based. There might be some definitions, but it's more like a solving problems. Similar to the written test, but you're more talking about like a specific grading scheme. I wouldn't say it's impossible. I haven't really looked at the exam for a while, so I need to revisit that. But it's definitely possible. It's to say you have to pass certain threshold for the questions before you can get certain percentage of the marks. It's definitely possible.
No, I meant more in like you have to argue, is this right or is this wrong? Prove it, and
Yeah.
if you put the wrong thing, then
Yeah, exactly. Yeah. So if you it could be a binary choice first of all for the question. Let's say the answer is supposed to be yes, but somehow you answer the wrong. You answer the no part. In that way, you can still get some partial marks, but since you got the answer wrong in the first place, so the maximum you might get will still be just 50%. It's possible.
Okay.
Yeah. Yeah, I'll talk more about the exam in the last class. And also, I'll definitely give you guys a little bit more tips about which area you may want to focus a little bit more. I can tell you that top-down parsing is definitely something you have to watch out for. Okay. And also the composite visitor, for sure. You can also study along the way before the actual exam. Okay, so I think today what we're going to do is we're going to start right from scratch, so no recap from before. I just want to remind you guys, so just basically what we're doing here is more to do about automating the leftmost derivation or rightmost derivation that we spoke about earlier. So up to now, we are basically doing the syntactic analysis, but we are all doing things manually. Nothing has been somehow implemented in a computer using some algorithm. So that's really the goal for this last part of the course, which is to see how we can do some syntactic parsing automatically. That's something we'll see. And today, I'm just going to give you some intuition about the two different kinds of parsing, top-down and also bottom-up. And then I'm going to present to you the algorithm and then talk about some limitation. And also we do a little bit tracing, but there will be a particular exercise that's going to involve much more detailed tracing, for which I'm going to hand wave a little bit in today's class. And then I will ask you guys to really look at the detailed tracing in a video. Okay, that one's not very long, but it will be much easier for you to look at it offline as opposed to in class, right? Because that one does require very careful tracing about the variable values to appreciate the algorithm. Okay, so that's something for today. All right, let's now go over a little bit slides, and then we'll come back to this page. Okay. All right, so now we are basically starting from slide number 33, okay, right here. Discovering derivations. So derivations, as I said, is going to be what we learned earlier about doing manually leftmost or rightmost derivation. And now somehow we say discovering, that means we're going to implement some algorithm to discover the derivation, if any, automatically. If somehow we cannot really derive the derivation for a particular string, give it some grammar, we know that that string is not grammatically correct. If somehow we can discover the derivation, that means we can draw the parse tree, that that input string must be syntactically correct, right? So that's kind of again, it's like a binary decision we have to make. So when you see the algorithm a little bit later today, you'll see that the output can be either some syntax error or it might return a tree. Okay, so this is some context-free grammar, right? So if you remember part of your written test coverage about how we formulate the context-free grammar. We got variables, we got alphabet, we got the rules, and also got a start variable, right? Things like that. We're going to see all these today. And also, we're given some grammar, and also we're given some program. And a program, I'll just say P, studying for program, is simply just a string, okay? A string. A new line can be a string, right? New line can be part of the string. But I can think about it as a single string, theoretically. All right, let's go over a little bit bullet points, and then we'll definitely get to the visualization, which will be easier for you guys to learn about this algorithm for the first time. So far, before the written test, we were manually trying to come up with the derivation. So if you remember this symbol over here, so we start with the start variable, whatever it is. And then by a series of production steps, could be one step, could be 10, could be 100, depending on how large the program is. So we start from the start variable, and eventually we want to go to some program. For example, let's say this. Okay, I'll just switch to example right away so you can see the correspondence. Let's say this. What we have is, we have a grammar right here, right? So we got expression, which can be expression recursively, plus some term. And a term itself can be turned, again, recursively, multiply some factor, right? You can definitely study the grammar yourself too, okay? So this will be input number 1, and also we got input number 2. And input number 2 is simply a plus a parenthesis multiply a, right? So given input number 1, input number 2, what we want to do is to find a derivation or a parse tree from there. And by the way, this is just a parse tree, which we can take a look a little bit later. Right? You can also look at that too. So that's what we are looking for. So you can think about eventually we want to say we start from the expression, which is the start variable. And then we're going to do a number of derivation steps. It can be either 1, it can be 0 or more. It could be that actually it should be 1 or more. Definitely, because you might need at least one derivation step to go from expression and then maybe to this, and then from expression here, maybe again to this, etc. Right? So this will be the parse tree. Okay? Eventually, you want to get to the a plus a multiply a. Right? You can think about this is the input string. And this is the start variable. And this is what the program or algorithm is going to discover automatically. Okay? Derivation steps to be discovered. It'll be very similar, when you try to visualize, let's say enter the 4, you got a G run, right? To really visualize the string or grammar as a tree, something similar. Not exactly the same, but something similar. Because if you know that the string is actually grammatically correct, you can also present a tree at the same time, right? Okay, so that's one thing to note. Then let's go back here. Okay, a parser is going to automate this derivation process, right? Rather than us using hands. Okay, input is going to be tokens, right? So token you can think about here. This can be one token here, one token, one token, and one token, and one token, right? A sequence of tokens. And these tokens were generated from the previous phase for lexical analysis. And you can review maybe the algorithm from earlier. So basically each pair is going to be the token itself and also the syntactic category. So the example we did earlier was about the register example, right? So that's register is the category. But when we do the algorithm here, usually the category is actually quite obvious, so we don't need to mention that. But just for completeness, you should really pass both the token itself and also its category, right? Okay. Right, and the output is going to be either it's a syntax error or it's a valid derivation you can discover. In which case, it's going to be an abstract syntax tree, just a tree. All right, and now in the process of doing that, okay, so these are the ingredients about the derivation. Okay, I'm going to go over that, also put that in the example. So abstract syntax tree that we're going to discover is going to contain 3 parts. Of course, the root, first of all. And by the way, the root, internal nodes, and also leaves or external nodes. So these are the terminology you guys learned from 2101 or 2011, the data structure course, right? So for that one, I'm not going to bother you. But in case you got any doubts about these, you may want to do a little bit on your own recall about these terms. Or you can drop by my office hour. I'm happy to go over them with you. But for now, I just assume you know what each of these terminology really mean for the tree. All right, let's now talk about these very quickly. Right? So abstract syntax tree, for example, let's say this is one abstract syntax tree. Let's talk about the 3 ingredients. Okay? Let me just write them down first. So we got the root, also we got internal nodes, also we got external nodes or leaves. So these are the 3 ingredients. Okay, let's say the root. The root right here. This simply corresponds to the start variable. You can see for the grammar, this is the start variable. Okay, so this is the start variable. Okay, that one's pretty straightforward. It's always the root of your abstract syntax tree must be the start variable. And then we have internal nodes. These are more like a recursive cases. So internal nodes could be, for example, the turn over here, and also factor over here, right? Everything. So let me just try to maybe confine them. So basically, starting from over here, right? Basically everything except for the leaves. Yeah, something like that. Okay, so these are the internal nodes. Basically, they are just the variables. And if you look at the slides, it will simply say a proper subset of the variable, which means the set of variables you have in the internal nodes don't need to contain all the possible variables, of course, right? Some variables may not be used. And finally, we got external nodes. External nodes right here, right? So for that one there, you can see here we got A plus A times A, right? It's like individual tokens. If you combine them together, you're actually going to get, oh, by the way, sorry, also got these 2, right? Parentheses. Right? So these are the terminals. Okay? If you do some kind of traversal of all the leaves, you're actually going to get back the original string. Some traversal on the leaves should give back. Oh, I'm sorry. Give back the input string. All right. Yeah, shouldn't be too difficult, right? Doesn't matter if you're doing top down or bottom up, it's always going to be these 3 ingredients. The root, internal nodes, and external nodes. All right, we're going to discovering some grammatical connection. Okay, so let me see this one here. Yeah, grammatical connection. So what this means is, for example, right? And this might be something you already know when you did the manual exercise. For example, if you look at, let's say, this particular layer, let's say this one here. If you look at just this one layer, right? So if you're going to recall back in 2021 or 2011, the data structure course, we talk about you can divide the trees, the tree nodes in different layers. You can say we start with layer number 0, and then we got layer number 1, layer number 2, layer number 3, layer number 4, etc., right? Different layers. So now I'm talking about, let's say, these two consecutive layers, L1 and L2, just for example. And you can see turn and also turn star factor. So these are somehow connected because you do have one grammatical rule right here. Right? That's what I meant by grammatical connection. Okay? I'll write it down. So you can think about that's the corresponding grammatical connection. Okay? So you can think about between L1 and L2, the reason that we can really say this is a valid parse tree because they correspond to some production rule. Grammatical connection, production rule. And as we'll see very soon today, in the actual algorithm for the top-down parsing, so in every iteration of the discovery process, we will actually have to try it out different production rule. That's kind of interesting part, okay? And if you actually want to dive a little bit more into the algorithm, you may want to look back to 3101, a very basic graph traversal called depth first search. Okay? That might be something you will find some connection to, okay, when we do the top-down parsing. I'll try to highlight something to you as well when we get there, okay? Okay, so that's about grammatical connection, and then let's see. Okay, so now we got two different approaches to parsing. Okay, so we got either top-down, or we might get bottom-up. Right? I'll give you some visual about roughly how they work. So bottom-up parsing is something that I will assign some study for you guys to do asynchronously, but of course you can get back to me if you got any question about the bottom-up parsing. But what we're going to discuss in the lecture will be top-down parsing. Okay, but you can look at the bullet point a little bit later, because these two may not make much sense at this point since you haven't really seen them concretely, not yet. Okay, but what's going to happen is somehow we're going to have, so this W over here is really some words, right? It's going to be a mix of the variables and terminal, right? This will be whatever word we are trying to do. And somehow we want to identify the production rule, somehow that's going to work to go with the derivation process. That's roughly what's going to happen iteratively. So we don't really try to implement the parsing algorithm recursively. We don't do that. It's more iterative process. So it's a while loop. Okay, so this, okay. So slide number 34 is the algorithm entirely over here. It's not very long, but it's actually rather complex. It definitely will take us quite a bit of study. So what I plan to do today is, before the break, I'm just going to give you some quick intuition about how the top-down parsing is going to work, very quick. And then we might go over a little bit about certain part of the algorithm, and then we'll do a little bit tracing, just for some simple one. The more complicated one, I'll leave you guys to maybe study some quick video before Thursday. Okay? And then we'll continue with the other discussion for the top-down parsing. It's quite a long discussion, so we're going to just continue. Okay, one moment. Okay. Let's now talk about top-down versus bottom-up. Okay. Basically, the input is going to be the same for both the top-down and the bottom-up. Okay, top-down means that you want to go this way, right? And bottom-up means you want to go this way, obviously. Okay, but we want to give you a little bit more intuition. In both cases, you're going to get input grammar for sure. And also you're going to get the string that you want to parse. Let's say the string might be just the same. But eventually, the parse tree that you're going to build, either from bottom up or top down, should be the same. Okay? Should be both are valid approaches. Yes?
Is the P for the parsing, top-down parsing and bottom-down?
Bottom up. Bottom up.
Bottom-up parsing? So we have the leftmost derivation and the rightmost derivation. Can we say the topmost derivation and the bottommost, or we don't use those? We use these ones instead?
We use this one. But as we'll see, the top-down parsing is really doing the leftmost derivation.
Okay.
It is what it is trying to do. Okay. I think that'll be good for now to kind of remember. That's something we'll see anyway. Because the way you're going to keep track about how to really do, we'll see. Okay. But this one here is really about leftmost derivation. Okay. But for bottom-up parsing, not exactly rightmost derivation. So let's not confuse that. Okay, just for the top-down parsing. Okay. All right, let's have a little bit intuition. To start with, we know that this one here is the start variable. And it's very important for you to also see that we're going to start with the start variable for sure. Okay, we'll talk about top-down. Okay, so that means when you start with, let's say, expression here, how many ways for you to really proceed? You can either go for this way here, or you can go for this way here, right? You got two possibilities. And since this one comes before this one here, so we might just do number 1 followed by number 2. It's a little bit like a depth first search, right? For depth first search, you're trying to traverse all the nodes in the graph, and then every time you have visited some node, you'll try to mark the node to be visited. When you backtrack, when you want to go for another route, because the current route actually hasn't really reached to the right place for you to go, and you want to backtrack. In that case, you want to somehow mark, you want to check to see if the node has been visited already. If it hasn't, then you go for that. If it has been visited, you don't visit again. Right? Things like that. We'll do something very similar for the parsing. Okay? So one thing you want to remember is for these two. Okay, for these two. And what, okay, write it down. For each occurrence of expression. Because you can see the expression here is the left-hand side for both production rule, right? You can see there's one occurrence for expression here, there's one occurrence for expression here, there's another occurrence, and that's another, one, okay, let me just say 1, 2, and also 3. Okay, so these are the 3 occurrences. For each one of them, you will have to keep track separately about which production rule has been tried, either 1 or 2. It is possible for some of them, you may have to go for 1. And for some of them, you may have to go for 2, depending on what the shape is for the input string. Okay, I'll write it down. For each occurrence of expression, keep track of whether production rule one or 2 is applied. All right, like that. If 1 doesn't work, you got to try for 2. Okay? For example, if 1 doesn't work, you got to backtrack and go for 2. For example, if 1 doesn't work, try 2. Okay? Oh, I should say one more thing before that. Okay? If 1 doesn't work, backtrack. And try number 2. Okay, so backtrack over here is very important. I'll talk about backtrack a little bit later, either Thursday or maybe next week. Backtrack. Okay, it's a very important term. Okay, let's see over here. Expression. Okay, let's see this. You can see this right here. Here, you see expression here. We go to the turn. You can see turn over here corresponds to number 2. What does that mean? It's not really number 1, right? First of all, let me mark it. So this rule over here is actually number 2. What that suggests is we should have already tried number 1, which would be expression plus turn. But somehow following this as the first step, as the derivation, is not going to give you the string ultimately, somehow. So what we should have done is we got to backtrack and decided that the very first step for the derivation should be go to the turn. All right, so I'll write it down. So the 2 over here tells you that production rule one should have been tried, because we always try 1 followed by 2. Okay, should have been tried, but could not work. So we backtrack and use production rule number 2. On the other hand, you can see for this particular one here, you can see expression using expression plus turn. That's exactly production rule number 1. That means we're going to use it first, and then it turns out this will be the right path to go. Right? You always got to try different production rule to see what will be the sequence to really go. Right? And for this one here, you can see again, this one here, you can see expression to turn. Production rule number 2. That means 1 has been tried but didn't work out. So backtrack again. Right? So this one here is another place where backtrack happened. Another place where backtrack, sorry, I'm just running out of space. Star. Backtrack happened. So we'll take a short break very quickly in a moment. So we're going to, after the break, I'm going to show you the algorithm, and then we're going to see exactly how to do the top-down parsing. What you will see is we always start with a start variable, and then we're just going to say, well, let's go for 1 here. And once we go for 1 here, we're going to try to choose the leftmost variable, leftmost derivation, and for that one there, which is expression, we're going to choose again this number 1 here, and so on. We're going to keep choosing the production rule and try different combinations until we can find the right sequence of the production rule. So that means lots of backtracking may be expected. Okay? But everything can be automated. That's a good thing. If you want to do this manually, as you will see in the tracing video I'm going to publish to you, it's a very tedious process, but you will have to know how to do it. All right? All right, that's about top-down parsing. You just got to keep trying different production rule. And at every instance for the variable, you have to make sure you have to keep track, like which production rule has been used. So each occurrence. Okay, that's very key. Okay, for the bottom-up parsing here, is actually going to be exactly the opposite direction, right? So we kind of start, for the top-down, we start with the start variable and go here, right? Top-down. For the bottom up, we're basically going to say, let's look at the string over here. And then we'll try to somehow process the string here to as long as we can. And maybe try to see if we can identify a certain pattern from there. As soon as we can identify a certain pattern, grammatical pattern, we can reduce that into the variable. For example, you can see here, when we look at the A over here. If we are trying to do bottom-up parsing, we're going to look at A here. We start with it, and then we know that A can be reduced into factor. Because we know that we can go the opposite direction, as you can see. Because a factor can produce A, so A can be derived or reduced into factor. Okay? It's a different direction. So think about A over here is reduced to. Of course, I'm trying to present in a very simplified way just to get some intuition. When you actually study the actual lecture, we need a bit much more details and precision. Okay? And then once we get to the factor, you can see that can be reduced into term. Term can be reduced into expression. So as far as A is concerned, we are okay for now. And then we can see that plus itself is just a token, right? And plus over here. And then we try to do the next input, which is A. A can be reduced to factor. Factor can be reduced to term. So now we got expression plus term. And now this guy over here can now be reduced into expression. You can think about every reduction we're doing also correspond to some production rule. Okay? One more insight. When you do top-down parsing, you go with one variable here and go apply the production rule. Let's say I'm here, and then I'm trying to apply the production rule, which is here. I have the branches like that. So going top-down. On the other hand, for bottom-up parsing, I may have expression plus and term so far. That's kind of the different different subtrees I have already built. How can I combine them into another bigger subtree? In that way, I look at these, and then they will match the right-hand side of this particular production rule, and then I'll do the reduction to expression. So I'm going bottom up. Okay, just different direction. But we're still using the same set of production in the same grammar. So that's why though both parsing algorithm will just work, it's just a matter of style, really. Okay. Okay, so let me say one more thing, and then we'll take a very short break. Okay, top down over here is from thinking this way. So you talk about some production rule. Usually, you simply got some variable and then produces some string, W. Right? That's kind of from the formulation for the context-free grammar. So for example, here, V could be expression. And the W here could be a mix of the variables and also symbols, right? So V and W. So when you talk about top-down, you're really talking about given V, how you can go to W. All right? And for bottom-up, it's really about if I'm already having some W, for example here, this is more like a W. How can I go to the V that will produce it? Okay? Just different direction. Either you go from here to here, or you go from here to here. Okay? Either produces or get reduced to. Okay? All right, just intuition. All right, we got exactly 40 minutes left, just about halfway. Why don't we take a very short break by taking attendance, and then after the break, we'll take a look at the algorithm. Okay. All right, so let's now talk about the top-down parsing algorithm. So again, you will see on slide number 34, so that's the algorithm. It's more like a pseudocode. Of course, it's not really particular to Java or C, but I think the logical idea that's expressed over here will be enough for you to actually implement it in a programming language like a Java, which will be your assignment number 3. But as I said, I'll rather we cover today and also Thursday with some basics before we actually release the assignment, and for you to give a try. And again, I'll push the deadline to as far as possible so you can get enough time to experiment the implementation yourself. All right, let's now go over this algorithm here. Just talk about the general structure and have some high-level idea. I may not dive directly into each line, but at least block by block, just for you to see what's the logical flow over here about the parsing algorithm. And then we'll do one tracing to identify the limitation for this algorithm here right away. And then the more tricky tracing on a larger input is going to be left to you. Okay, something I will also give you some video solution to go through. All right, let's now take a look. All right, so this is the algorithm. Okay, right here. All right. And then, so of course, when you are given, the algorithm is going to take input. First of all, the grammar, right? The grammar right here, right? You can think about this will be the grammar and input grammar that's given. And when you see assignment number 3, you will see some particular way to represent this grammar in Java. It's just one way. Okay, you will see that. But for now, just focus more on the conceptual level, just to understand what's going on. Of course, you'll be given input the grammar and also the string, which I didn't really put here, but I'll put it right here. Also, the input string. And that one there, you can see this one here. All right, just the same string. Even for simple string like this, it can already involve quite a bit of tedious and complicated tracing. So I think that would be good enough for us to see the idea. So you're going to pass these two things and then call this parsing algorithm that's top down, and then output is going to be either the root of a parse tree when the string is actually grammatically correct with respect to this grammar, or it could be a syntax error, either way. Right? So only two possible outcomes. So we're going to see that. And the way to look at this is it's an iterative algorithm. So while true, of course, you may not like this style. Actually, I don't like this style either, personally, because in some way you're saying that we might run into infinite loop, right? While true. We are relying on the algorithm, the loop body itself is going to return at some point, right? So not the best style, but that's something I adapted from some textbook. So I didn't really change it fundamentally, yeah. You can definitely change, yeah. So I think for your assignment number 3, you're more than welcome to really copy and paste this or whatever you like. You can feel free to adapt this. I'm not the original inventor for this algorithm anyway. So that's really a very standard one from the textbook. So for the assignment number 3, you can just study through the algorithm. If there's any part you think you can rewrite using something that's more understandable, something that's more efficient, feel free. No problem. Okay. So this part over here, let me start with something called initialization. So this part here is the initialization before the loop. So on this page, we don't do any tracing just yet. I just want to go over with you about the algorithm. Okay? So this will be initialization. And then we go into this loop, which may run indefinitely. All right, just notice that. And there are two possible branches. There are two possible scenarios where we might backtrack, meaning that what we have done so far doesn't really work. So we're going to go back to where we were originally branching out and try another branch, if there's any other branch, right? Conceptually. That's exactly what backtracking really means, also for your depth first search algorithm. All right, so let's look at the different variables that we're going to keep track. So we have something called the root, right? That really corresponds to one of the ingredients for the abstract syntax tree. And we've got something called focus. You can think about the focus over here as like a current pointer. If you remember, maybe back in your data structure course, if you want to traverse from left to right a linked list, you would say, I would say current equals to the head of the node. And then I'll keep moving the current to current.next, right? Current is like a pointer about where I am in the list or in the tree. So the focus over here is really something about current. More or less the current. All right? And then we're going to have another, we're going to use a stack, okay, called trace. And then we're just going to push the null value into the trace. Again, it's just the algorithm that's kind of presented in the standard textbook. If you don't think you really want to put any null value to begin with, feel free to experiment. Not a problem. Okay? Of course, you might have to modify certain parts of the code accordingly, but that one I'll leave to you. And then the word over here is a little bit like the Lexer algorithm we did earlier. We're going to get word by word from the token, right? For example, if you look at this one here, is really I'll put it here. The input. The next word is going to return back to you token by token. So let's say for this one here, we actually got several. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, like that. So the first one will be left parenthesis plus, and then we got A plus A, closing parenthesis, multiply, and A, right? So the first word to return will be the left parenthesis, right? And then, so we got the word, next word, okay? Okay, so that's about initialization, okay? I'm gonna trace it a little bit later, but for this page, let's just look at how the algorithm is gonna work conceptually. So after this, we got branches over here. So we got branch number 1, we got branch number 2, also we got branch number 3, we got branch number 4, okay? Let's not look at the nested if then else just yet. I think it will make a little bit more sense once we trace some concrete example. But I'm gonna highlight these branches. So let me just do the following. Okay, so this is the first branch, focus. And then second branch, this one here, and also this one here. All right, so these are the 3 possibilities overall. So for each iteration, we're going to go for either this one here, in which case we may actually have done some work over here, but nothing has been conclusive. So we got to go for the next iteration. That means we got more work to be done. Or if we go here, that means we got to backtrack. That means whatever we have done so far, it's not going to work. So we got to backtrack. This branch over here tells me that if the current word is actually matches the focus. What does that mean? So the word matches the focus. So let me just try to, oh, you know what? Let me start from the top. That'll be a little bit better. Let me start with this one first. What does this really mean? This really means if I am trying to build a tree, let's say this is the tree I'm trying to build so far, right? The tree. And then the focus is really pointing to some node in the middle. Okay, the focus, right? It's really the current. It's pointing to a particular node. And we're saying that this node here is a variable. For example, it could be a term. For example, this can be a term. Right? If the current focus is actually turn, that means we have to somehow choose to say either we want to go for this particular production or we want to go for this production, either way. All right, so that's one scenario. So the turn over here that we might either go for rule number 1 or rule number 2, whatever that's not used just yet. 1 or 2, whichever not used. All right, but we'll definitely trace a little bit more into detail. Yeah, question?
So in this example, grammar is factor rule the only one that could potentially not result in a variable because it can result in A?
Yeah, that's quite right, yes. Yeah, just different rule, right? Of course, you know, for factor, it might be that, so, okay, let's say for factor here, by default, you're going to try with this one first. If somehow this one here cannot lead you to what you really want, then you may have to go try in this one here. And this one can also not let you get to what you want. That means the factor here is not the way to go. You got to backtrack even further. Exactly, yeah. Yes?
So focus stores the rule that is not used?
Ah, good. Focus store the node. Good question here. You actually brought up something very important, which is something you have to watch out for when you implement it, right? So the focus here is really pointing to a node, current node, not a rule. On the other hand, when you actually try to build this tree top down over here. So for example here, when you actually do expression here, since I'm choosing to go for term, well, let me say a little bit differently. Let's say here, let's say I'm here, expression, right? I'm here, expression, and then I choose to go for this particular rule. And then I got expression, I got plus, I got term. Exactly this one here. Let's say as far as this level is concerned, I have already used rule number 1. For whatever reason, if it turns out whatever I'm building as a subtree over here is not going to really match what I'm looking for. In that way, I should really backtrack and try with rule number 2 instead. So that means at this level over here, you should also keep track about which rule has been used already. If one has already been used, when you backtrack back to the original place, the same place, you have to use rule number 2 instead. So you have to somehow keep track about which rule is used at every level. Okay, I'll write it down. And then at each level, keep track of the rule being used. Okay, keep track. Okay, for the details, we'll look at that a little bit more when we get to the tracing. Okay. And then over here, we're going to get the second scenario will be if the if the word matches the focus. What does that mean? That means we actually got, for example, let's say here, if the current word, let me visualize that. Okay, this one here, that means we actually got a tree that we built so far. And then we actually got the node, that's actually the focus. And this node is actually a symbol, for example, like an A over here. So if that's the A over here, we're going to handle it a little bit differently because now we know that's a terminal. It's more like a leaf over here. So we should not really continue with the derivation from this branch. So what we should do is we should somehow maybe go back and then to do the next one. Okay, just a different handling. Okay, my point is either the focus here, it may be a node, maybe a variable, or it might be a symbol. We're going to handle that differently. That's something we'll see. All right, finally, this will be the ideal case, right? So this one is telling us if there's no more word, it's the end of file. So let's say we are now already at the end of the input sequence of tokens. So we don't have any word to really read, and then the focus right now is actually simply null. So that means we are now just pointing to nowhere. Maybe, so null here, got to be more careful. The null here may have to do with the null value over here. Okay, got to be careful. So that's why we put a null here. Okay, so null here simply means we have already processed all the. So null simply means so all derivations so far actually work. And then given that there's no more token to be handled, so we know that the tree that we have built so far is really the final parse tree. Nothing else to be added, okay, conceptually. All right. Okay, let's now take a quick look of some example tracing, okay, and then we'll see. Okay, this one hopefully is not gonna take too long. This one here is really just for you to get a feel. And then the actual tedious one that's kind of longer is something you guys will have to look at, ideally before Thursday. Okay, it's not gonna take that long, okay. All right, let's now take a look. So we got the algorithm here, and then we want to, let's say, parse this. I deliberately take out the parentheses, just make it a little bit easier. Okay, so now got A plus A times A. And let's now do the initialization right here. Okay, let's now do that right here. Okay, initialization, we are going to have basically the root. The root is going to be a new node for the start symbol S. We know that this is a start symbol. So root is really pointing to a node which stores the variable expression. All right, we'll start with that. How deep the tree is going to be, we don't know. And then we're going to set a focus to be the root. That's where we start with. So I'm going to say the focus is actually going to point to the root. And also some empty stack called trace. Okay, so I'm going to put a stack right here. It's called trace. And then we're going to put the null value to begin with. All right, and also the word will be the next word. Right? So here we just start with A. Okay? So you can think about the word. I'll put it here. The word right now is just A. All right, that's the initialization before the loop. All right, so let's now run the very first iteration. Okay, the first iteration, so we're going to see which branch we're going to go for. Either this branch, or this branch, or this branch, or if neither, backtrack. Guys, which branch? It should be an easy judgment. 1, 2, 3, 4. Which condition will be satisfied, for example? For example, how do you evaluate this first condition?
Would it be 1 because we haven't reached any leaves yet?
It will be 1, but not for the reason you just mentioned, right? So we'll only go for 1 if this condition is true. What's this condition? The focus should be a variable. What's focus? Expression. Is expression a variable? Yeah. If that's not a variable, it could be A, or can be parentheses, right? But it's a variable. All right? So that means this one here is going to be satisfied. So we go for that. All right? Good. So now for the very first iteration, I'm going to actually use here. So for the very first iteration, this is satisfied. Okay? And then I'm going to go for the nested if right here. What does it do? It says that if there exists some unvisited or unapplied rule that will be from focus to something, then we should do this. The focus is really expression here. It really has 2 rules, 1 and 2. Right? 1 and 2 here. Both of them are unused, so there's at least 1. So we choose number 1. All right? And the way to look at that would be, you can see the pattern matching. So we got focus right here, right? So this one here, I can analyze a little bit for you. You can see that one there is expression produces expression plus the term. So this part here is the focus. Beta 1, beta 2, all the way to beta n. So you can think about this is beta 1, this is beta 2, this is beta 3. Just different components, right? Each component can either be a variable or a symbol, all right? And what we do is we are going to actually do each one of them. This one, first of all, create different children for the focus, right? So beta 1 will be expression. And beta 2 will be the plus. Beta 3 will be also the term. Right? So child number 1, child number 2, and also child number 3. Right? And then we're going to push over here. And notice that this one here, right? I'll make it a little bit bigger. Right? Do you see anything missing? Or is really complete list to the right of the production? Something, huh? Yeah, exactly. It's intentional, it's not typo, all right? It's because currently we are handling beta 1, so we don't need to put it. Okay? Beta 1 is somehow missing. Okay? Intentional. Okay? So what we do is, and also you gotta put in the reverse order. So when you pop from the stack, you'll get exactly from left to right, right? Just a little bit tricky. Well, not really tricky, just a little bit trick. For the last in, first out. So what we do is we're gonna go for beta 3, beta 2, okay? So we're gonna put turn, and also we're gonna put the plus. That means later on, once we have handled this particular branch built on subtree, what should we do next? It should be the plus and then the turn, right? Okay. And the focus should now be assigned to the beta 1. So that means the focus, rather than pointing to over here, is now going to point to here. And that will be the end of this particular branch, and we're done for the first iteration. All right? Now, before I do the second iteration, I'm not too sure if any one of you already see some problem over here. If not, that's okay. It's a bit tricky to see from the first iteration. Let's do the second iteration. All right? For the first iteration, we're good, about initializing the node and also find a production rule that's unused and etc. Okay? Now, I'm going to use a different color for the second iteration. That's actually very important to notice. Okay? So now I'm going to use, let's say, maybe green. Okay? So for the second iteration, we are still, so now the focus is right here, right? Focus. And at the beginning of the second iteration, we got 4 choices. Either we go for number 1, or we go for number 2, or go for number 3, or we go for number 4. Which one do we go for? Again, you got to evaluate the branching condition here, right?
Yeah, I was going to say you have to, it's the same because you have a variable stuff.
Exactly, yeah, exactly. That's what I wanted to hear. Yeah, just want to make sure you guys are okay. Otherwise, I'm going too fast, right? So you can see focus over here is expression, which is a variable. What would it do? So here, so now that means we're going to go for this one here, right, for this current iteration. Is there any unused row? So this is also just let me finish this and I'll answer your question. I also want to emphasize the point again. You can now see we are now trying to handle expression again, the variable for the second time. So now to really see which rule is not used, right? You got to watch out when you do the implementation for assignment 3. From the previous iteration, we chose rule number 1, so we get to here, right? It's only for the previous one. But now, when you are here, you're deciding which rule is unused to really go further. You cannot consider one as being used already because they're at different level. Right? Okay? Let me write it down and I'll answer your question. You want to think about, you can think about this is 1 and this is 2. You can see the blue one really correspond to this particular derivation. And the purple one is correspond to what we're going to do right now. So you got to keep track of them separately. It's a very important part to get right for this algorithm. You want to keep track. All right? Yeah, question, please.
So in this case, if you go from expression to expression cross term, what prevents the other expression from keep using rule number 1? They just keep going and going and going and going forever.
That's a very good question. Actually, you answer exactly my question. As you guys can see, in this slide, there's no way for us to stop over here, right? Because what we're doing here is really leftmost derivation. We always choose the leftmost variable. Let me continue. Okay, that's very good. That's exactly the problem, okay? So here, basically, if you do one more, you're going to have expression, also plus, and also turn. And then focus rather than here is now going to be over here. And then you're also going to put the turn and also plus onto the stack, right? Basically, you got to keep going and just go for expression, expression, expression. It's basically not going to terminate, all right? The very reason for this, I'll give you the answer, okay? What we're doing here for this algorithm, we're basically trying to do leftmost derivation. because we keep finding the left and the left and the left. Once it is done, we go to the next one, right? And the grammar here is not going to be suitable for that because the grammar is so-called left recursive. You can see expression here, you got recursion right away. And also you got turn here, you got turn right away, left recursive. When you got some algorithm that's going to do leftmost derivation, having a left recursive grammar is going to cause termination problem. So now how can we fix it? Well, apparently you can fix it by two ways. Either you can simply put this guy here into finding rightmost derivation instead, right? In that case, this left recursive grammar is not going to cause you trouble. Or you're going to provide a grammar that's not left recursive, right? Either way. Okay, and this grammar over here is left recursive. So the problem is, really is, you are basically using a left recursive grammar, grammar for a leftmost derivation algorithm. They got termination problem. So what we're going to do is, we don't want to change this algorithm. Okay, we want to keep it. However, we want to give you a different version of some equivalent grammar that's not left recursive. And what we will see on Thursday is, since we cannot really control about the input grammar that's given by the user in general. So given any grammar, you will first of all have to identify if this contains any left recursion. If it does, you will have to remove it by doing some fixes, which we'll discuss on Thursday. Okay, let me recap. Top-down parsing algorithm tries to find the leftmost derivation. Because of that, you cannot really give it a left recursive grammar, in which case you're going to run into infinite recursion, infinite loop, basically, like what we have seen. All right? So this is going to be infinite loop. The way to fix it would be, we're going to give you a grammar that has no left recursion. Okay? That's what we'll do. Alrighty. Okay. Just a little bit more about left recursion, just show you very quickly. So there are two ways to really, for a grammar to contain left recursion. It can be either direct or indirect. For direct, basically you can see expression, and then the leftmost variable just the same, repeating, right? Also turn over here, you can see turn appears right away as well. All right? So that's left recursive. And for indirect, you will actually have to follow through the path for the variable. For example, you can see A go to B, B go to C, and C go back to A. There's a cycle there, right? And also you can see A goes to B, B goes to C, C goes to D, and also D, one of them can go back to A. This cycle there. As long as you can build some cycle among the variable production, you know that there's left recursive. We'll talk a little bit more about this, about how to remove it on Thursday. Okay? Got about 5 minutes. Okay, I think this will be good. Okay, so now I want you guys to give it a try, the best you can. Okay, so let's say this is the grammar. That one is not left recursive anymore. It's right recursive. Why? You can see expression here. You don't see expression here, so that's not left recursive for here. Also, you can see expression prime. You don't see expression prime right here, but you see expression prime at the rightmost. So that's right recursive, right? But this grammar here is equivalent to the grammar that contains left recursion. It's equivalent, okay? So now, so this will be the grammar to use. And if we try to trace the top-down parsing algorithm using this grammar here, we will be able to build a parse tree accordingly. So now this is what I want you guys to do. I got about 5 minutes. Okay, why don't you spend about 3 minutes? What I want you to do is this. Can you please try to take this string over here and then build a parse tree from there using this grammar manually first, and then it'll be a little bit easier for you to understand how to do this automatically. Okay, draw the parse tree. And then I'll give you a little bit hints over here. This grammar is actually a little bit peculiar. Once you see the actual parse tree may not be as intuitive as you might think, but it's going to work, right? So you want to think about when you actually have this part over here, right? Let's say, for example, A here. Oh, by the way, you can see this epsilon in the production row. We call it epsilon production, which means when you got expression prime, you can choose to produce just epsilon, right? So you can think about here, A here can be thought about as A followed by epsilon. That's a key about drawing the parse tree. That's a little bit hints to you. All right? So guys, why don't you take about 2 minutes or so just to try to draw the parse tree, okay? There will be another exercise I will assign, which is to do the leftmost derivation for that, which I'll give you the solution as well, okay? And then after this, that'll be it for today. And then I will assign you to actually try to trace this particular string using just this algorithm that we spoke about, about the different variables and also the cost stack. And then I'll give you the video solution. This will be a very important exercise to really get through, ideally before Thursday, okay? All right, parse tree. That's one thing at a time. If you don't mind, I can help you a little bit in the beginning. Okay, how about this? Why don't we start with expression? For sure, that would be the start variable. Okay, let me start with that. And then, let's say I can tell you that what we're going to use would be, well, you only got one choice. Turn expression prime. By the way, if you actually got expression, and then you try with the turn, and also expression prime, and somehow this one actually doesn't work, so you got to backtrack. But if this is already the start variable and the root, you try to backtrack, what does that mean? Syntax error. There's no other option for you, all right? So this one here, I'm going to put turn and also expression prime. Okay, I'll start you with. And feel free to also use the epsilon option there. Oh, 1 minute, and then it just takes me about 1 minute to give you the solution. Okay. It's good to give it a try. I presume in some way when you're trying to do this manually, you're also going to try different production rule combination. That's exactly what the algorithm will do. It's just that it will do it faster than you would, also more systematically than you would, also, just tedious, right? You wouldn't feel bored. We will feel bored about doing this. Anyone done already? Okay. How do I go after this?
I went to factor thing.
Aha, sounds very promising. Okay, why don't we try? Factor. And then turn prime. And factor will go to A. Turn prime will go to epsilon. Okay, good. Okay, seems like you guys are on track. Very good. Okay, I'll just give you a solution. And then under expression prime, we're going to go for plus turn and also expression prime. Plus is already the symbol. Under the turn, we're going to get factor, turn prime, and we got A, we got multiply, we got factor, we got turn prime. So this will be A, this will be, okay, give me 2 minutes, please. That will be epsilon, and this one here is also epsilon. So if you look at that, look at the leaves. A, epsilon, plus A times A, epsilon, epsilon. So you will see that just the leaves. A, epsilon, plus A, multiply A, epsilon, right? So exactly A plus A times A, okay? That's a parse tree. And then one thing I want to say very quickly, okay, so you can think about something just as an observation. Apparently this term over here, eventually, with some derivation, is going to produce A, apparently, right? And also, if you look at this term over here, for example, that one there, we know that eventually it's going to produce this A times A. Right? You can see the A times A exactly as the leaves under that subtree. Right? Yeah, just one moment. So another exercise for you to try, partially at least. Leftmost derivation. Okay, it's going to be long, but I'll give you what I have already as well. And then I'm going to also let you go over the tracing, about tracing how this parse tree right here can be built using this string and this grammar over here and this algorithm. Okay, so try to do this before Thursday. It's going to be very beneficial to move on with the top-down parsing. Question, please.
Were we missing an epsilon in the end?
Yes, I agree. Thank you so much. Thank you so much. Thank you. Guys, thank you. I'll see you on Thursday.